All right, we're going to set up another linear programming problem. In this one, it's about a company that makes bicycles and tricycles for kids. So let's circle the constraints and underline the other important numbers that we have here. All right, so we know each bike and trike takes 30 minutes to make, to assemble, and bikes take 15 minutes to paint, while tricycles take 20. We also know there are 10 hours a day available for assembly. That's a constraint. Because that's like something about how much time we have in total, not an individual piece of information about a bike or a trike. Similarly, there's 6 hours available for painting. Then we know the profit on a bike is $20, the profit on a tricycle is $15. And finally, we know there's an order from a toy store for 5 tricycles per day. So I'm going to circle that, and you'll see why that's a constraint here in a little bit. And the question is, how many of each toy should be made each day to maximize profit? All right, so just like before, the first thing we should do is we should make a chart. So the two types of toys that are being made are bicycles and tricycles. And we know things about the time to assemble and the time to paint and the profit. So assembly, paint, profit. All right, so now we can fill them in. So for the bike and the trike, they both take 30 minutes to assemble. For painting, the bike takes 15 while the trike takes 20. And for profit, the bike gets $20 per profit and each tricycle gets $15 per. All right, so that's our table. We've listed out the two toys that are being made, the bicycles and the tricycles, and we've listed out time to assembly, the time for painting, and the profit for each one. Now we can define our variables, and remember to do this in complete sentences. And we can get this from the last sentence. How many of each toy? Those are our variables. So let's let X be the number of bikes made each day. And let's let Y be the number of tricycles made each day. And then we want to maximize profit. So find X and Y to maximize profit. And we can find the profit function from the table. So we know that profit is equal to, well, for each bike, we get $20, so 20X. And for each tricycle, we get $15, so 15Y. And so we want to maximize profit, but there's some constraints. All right, so we can get a constraint from a column of the table that we haven't used yet. So for assembly, 30 minutes each and 10 hours total. So we got to convert from hours to minutes or minutes to hours. It's up to you. I'm going to convert from hours to minutes. So it takes 30x minutes to assemble X bikes. It takes 30y minutes to assemble Y tricycles. And in total, we have 10 hours. And 10 hours means 600 minutes. 10 times 60 is 600. So that's a constraint based on assembly. We also have a constraint based on painting. So it takes 15x minutes to paint X bikes. It takes 20y minutes to paint Y tricycles. And we have 6 hours for that. And an hour is 60 minutes, so 6 times 60 is 360. There's one circled number that we haven't used yet. That's the 5. We know that there's an order from a toy store for 5 tricycles each day. So that means we know that Y has to be at least 5. So Y is bigger than or equal to 5. And this is from our standing order. And the only constraint we're missing is the one that all of these word problems will have. We know that we can't make negative bikes or negative tricycles, so X and Y both need to be bigger than or equal to 0. That's it. You might notice that we don't need to say that Y is bigger than or equal to 0 if we know Y is bigger than or equal to 5. So that's fine. If you just want to write X is bigger than or equal to 0 here, that's totally fine and that's up to you. I'm just going to write them both. That way I'll never forget it.